Hello and welcome to another digital logic design class. Today we're going to start chapter 2, Boolean algebra and logic gates. In the previous class, we spoke about binary systems, binary codes such as BCD, and at the end, we spoke about digital logic gates. Today we will continue with Boolean algebra, and we will show you the different rules of Boolean algebra and how we can utilize them to simplify logic gates. So we will start with a small introduction and a history of Boolean algebra. It was first introduced by George Boole, and he came up with a type of linguistic algebra that has three basic operations. We have and, or, and not. And these three functions form the basis of his premise and were the only operations necessary to perform comparisons or basic mathematical functions. His approach was based on a binary approach, processing only two objects, the yes, no, true, false, or on, off, or 0, 1 approach. Initially, he was ignored by a majority of his peers, but finally, Claude Shannon, he was working on his actually master's degrees, and he expanded on the idea of Boolean algebra, and he was a genius that came up with a lot of theories that we have in communication systems as well. So some basic definitions of Boolean algebra is that we have some postulates. The most common postulates used to formulate various algebraic structures are as follows. We have the closure. A set S is closed with respect to a binary operation. For every pair of elements of S, the binary operators specifies a rule for obtaining a unique element of S. So for example, we have natural numbers, n is equal to 1, 2, 3, etc. It's closed with respect to the binary operators plus by the rule of arithmetic addition, since for any A and B belonging to n, there is a unique C that belongs also to n, such that A plus B is equal to C. But obviously the subtraction operation is not closed, because if I subtract 4 from 5, 4 minus 5, we have -1, and it's not going to be a part of a natural number. And then we have the associative law. A binary operator like the AND operator, multiplication, on a set S is said to be associative whenever X and with Y and with Z is equal to X and with Y and with Z. For all X, Y, and Z. Or X plus Y plus Z is equal to X plus Y plus Z. And then we have the commutative law. A binary operator like the AND operator on a set of S is said to be commutative whenever X and with Y is equal to Y and with X. Or X or with Y is equal to Y or with X. By the way, these are and or operators. So we can write it like this. 1 and with 0 is equal to 0 and with 1, which is equal to 0. This is a proof for that. Or 1 plus 0 is equal to 0 plus 1, which is equal to 1. Some other definitions are identity elements. A set S is said to have an identity element with respect to a binary operation of AND on S if there exists an element of E with the property that E AND with X is equal to X AND with E. So 0, for example, 0 plus X is equal to X plus 0. and 1 times x is equal to x times 1. And then we have the inverse, a set having the identity element with respect to the binary operator to have an inverse whenever for every x belonging to S, there exists an element of y that also belongs to S, such that x and with y is equal to E. And then we have the distributive law. And for the distributive law, we use, if we have an and, for example, operation, both of them are ands, but shows differently here. We can have x and with y and with z, or x plus y and with z would be x plus y and with x plus z, or x and with z times x and with y. And then we have the axiomatic definition of Boolean algebra. We need to define algebra for binary values. And we have the Huntington postulates for Boolean algebra, which was introduced in 1904. And this is way before we had computers. All of these are the fundamentals of the computers that we have, computer systems that we have, that was actually started in the 50s, 40s and 50s. B is 0 and 1 and 2 binary operators, or and. The closure with respect to operator or and operator and. Identity element 0 for operator or and 1 for operator and commutativity with respect to the or and distributivity of over of and over or and or over and. So for example, as I mentioned, this star could be the and operation or the or operation. So x and with y or with z is equal to x and with y or with x and with z. And it's the opposite is also true. X or x and the or, not x or. Y and z is equal to x or y and with x or z. And the complement for every element x is x prime with x plus x prime is equal to 1 and x and with x prime is equal to 0. And we can easily prove this. So if x is 1, for example, x prime would be 0. So x plus x prime would be equal to, by just replacing, it's going to be 1 plus 0 is going to be 1. Or if x is 0, x prime would be 1. Again, it's going to be 0 plus 1, it's going to be 1. So no matter how we solve it, always x plus x prime is going to be equal to 1. And x and with x prime is going to be 0 and with 1, it's going to be 0, or 1 and with 0, if x is 1, it's going to be still 0. These two operations are very important. There are at least 2 elements, x and y belonging to B, such that x is not equal to y. That's the opposite. So for Boolean algebra terminology, did you write this down? Can I go to the next one? We have literals. A literal is a variable or its complement, such as x, y, z, or a, b, c. Or we write it like a, b, c. And a complement would be x prime, y prime, and z prime. Also a prime, b prime, and c prime. These are the literals. And then we have the product term, which is the and literal connected by the and, the dot. And we have the sum term, which are the literals connected by the or operation. Next, we have postulates of two-valued Boolean algebra. If B is equal to 0 and 1, and two binary operations of or and, or again, and the and operation, the dot is for and, just a reminder. The rules of operations and, or, and not are as follows, and we mentioned this in the previous class when we mentioned the and, or, and not gate. So 0 and with 0 gives us 0, 0 and with 1 gives us 0, 1 and with 0 gives us 0, and 1 and with 1 gives us 1. 0 or with 0 is 0, 0 or 1 is going to be 1, 1 or with 0 is going to be 1, and 1 or with 1 is going to be 1. And the not, 0 not would be 1, 1 not would be 0. And we have the closure and the identity elements as well. We showed the AND gate with this symbol, and we showed the OR gate with this symbol. The pen doesn't work. And the NOT sync was with this. We had the AND, OR, and NOT. This is just a reminder. So the other postulates of a two-value Boolean algebra systems are the commutative laws and the distributive laws, as mentioned. So imagine if we have three literals, x, y, and z, and we want to find x times, or x and with y or with z. Then according to the distributive law, it's going to be x, this x and y or with z is equal to x and with y or with x and with z. So this translates to this. Now, y plus z is 0. If we have x, y, and z, 0, 0, 0, x and with y is 0, x and with z is 0. Therefore, x and with y is going to be 0 plus x and with z, which is again 0. So 0 plus 0 or 0 or with 0 gives us. And we have that to the end. So for example, if let's say we want to find this one. X is 1, y is 0, and z is 1. And we want to find x and with y plus z. X and with y gives us 0. X and with z gives us 1. And 0 or with 1 gives us 1. Is it clear? Yes? Do you want me to solve an example, or is it clear? Just replacing the other postulate, next postulate that we have is the complement, and adding any number to its complement gives us the result of 1. So x plus x prime gives us 1. So 0, and the way that we could prove this, as I mentioned, just replace it with a binary value. So it's going to be 0 plus 0 prime, and 0 prime is actually equal to 1. So 0 plus 1 always gives us 1. Or 1 plus 1 prime, and 1 prime is going to be equal to 0. So 1 plus 0 is. And when we multiply them, we always get 0. So for example, if x is 0, x prime would be equal to 1. So 0 times 1 gives us 1. I'm sorry, 0 times 1 gives us 0. And so on. If 1 times 1 not, and 1 not is 0, so 1 times 1 not gives us 0 again. So in all situations, if you add a number to its complement, you get 1. If you AND it to the number, you get a 0. The sixth postulate is that the Boolean algebra has two distinct elements, 1 and 0, with 1 always opposite to 0. And some notes: a set of two elements. The plus is the OR operation, and the dot is the AND operation. A complement operator is the NON operation, and the binary logic is a two-valued Boolean algebra. Then we have the duality. the principle of duality is an important concept. This says that if an expression is valid in Boolean algebra, the dual of that expression is also valid. To form the dual of an expression, replace all OR operations with AND operators and all AND operators with OR operators. All ones with zeros and all zeros with ones. So form the dual of the following expression. If I want to form it, again, we would replace the ORs with ANDs and ANDs with the ORs. So first thing, we can expand it and we can have A plus B times A plus C. Now I can replace all the ANDs with OR, so I can say AB, this OR becomes an and this AND becomes an OR, plus AC. Which you can see here. It becomes AB plus AC. So here, the OR operation becomes an AND operation, and the AND operation becomes an OR operation. We have to be careful not to alter the location of the operations and the parentheses if they are present. So for example, again, X and with Y plus C. If we want to find the dual of this, we replace the AND operation with OR. So it's going to be X plus, and the OR operation with AND, YZ. So this is going to be the dual of the previous. Now, let's give them some numbers. So imagine A is 1, B is 0, and C is 1. If I solve this one with these values, A is 1, B is 0, and C is 1, what is the final answer that I get? One. It's going to be 1 plus 0 times 1, which gives us 1. What about here? What do I get? Again, it's going to be 1, 0, plus 1. And I'll solve more problems from the duality. Now, this table shows us all the postulates of Boolean algebra and the basic theories. And this is a very, very important table. This shows different postulates. You can see postulate number 2, x plus 0 gives us x, x plus x prime gives us 1, x plus x gives us x, x plus 1 gives us 1, and so on. And then we have different theories, theory 1, 2, 3, and you can see different postulates. And we can actually prove any of these theories with the postulates as well. I want you to take a good look at this. And I would solve some of them. And these are the basics, and you're going to have this table in your FE and also your exam. And you're going to solve the Boolean, any Boolean algebra that question that you have, you can use this table to solve the Boolean algebra question if you haven't. Now, let's do an example of different postulates, and let's continue with the Huntington's postulate, which defines some rules. The postulate number 1 is the closure. Postulate number 2 is x plus 0 gives us x, and x times 1 gives us x. Postulate number 3 gives us x plus y is equal to y plus x, and x times y, it gives us x, y times x, or x and with y gives us y and with x. Postulate number 4 is the distributive law. X and with y plus z gives us xy plus xz, and x plus yz gives us x plus y and with x plus z, or x or with z. And postulate number 5 is x or with x prime gives us 1, and x and with x prime gives us 0. So what is a theorem? A formula or statement that is derived from postulates or other proven theories. Basic theorems of Boolean algebra. Theorem number 1, x plus x gives us x, and x times x gives us x, or x and with x gives us x. This looks straightforward, but needs to be proven. So for the proof of this, we can write it like this. X plus x, we can write it as x plus x times 1. Because we have this postulate, we can use it. And we know that 1 is equal to x plus x prime. So I can replace this 1 with x plus x prime. Now, x plus x prime and with x plus x, I can use this theory here and write it as x plus x and with x prime. Again, we know that x and with x prime gives us 0. And we know that x plus 0 from postulate A gives us x. Now that we are sure that we have this theory, we can use it and for the further proofs as well. So next, we want to prove that x and with x is equal to x. Again, we can use the postulates. We can add that to a 0 using postulate number 2, because adding a 0 to a Boolean algebra, it doesn't change anything. It's equal to itself. So x, imagine this is x plus 0 gives us x. And then we can replace 0 by x and with x, which is postulate 5b. And then we can distribute that. We can say it's x times x plus x prime. And we already know that x plus x prime gives us 1. And then x times 1 gives us x. So the second theory was also proved.
QED.
I'm sorry?
What is the QED at the bottom?
Good question. I forgot.
That slide at the very bottom of the proof.
Yeah, I forgot.
Oh,
Sorry. What?
I think it's Greek or Latin.
Yeah. Oh, good question. But I remember what it meant, but yeah. I would look into it and get back to you in the next class. So let's solve a practice problem. Oh, let's do the last proof and then we will go to the practice problem. So this one, we want to prove that x plus 1 or x or with 1 gives us 1. So we can use postulate 2b and have 1 and with x plus 1, and imagine this is our x. And then we would have 1, and we can replace 1 with x plus x prime, and then multiply it again and with x plus 1. And then we can use again 4b, the distributive law. And we know that x plus y and with x plus z is x plus yz. So it's going to be x plus x prime 1. And this is equal to x plus x prime times 1 is equal to x prime, and x plus x prime is equal to 1. And we can do the same thing for x times 0 is equal to 0 by duality. Now, let's solve a practice problem. And I'll show you that we can use these proofs. Sorry, my pen stopped working. F is equal to A, B, C plus A prime plus A, B prime, C. We want to simplify this using, did you write it? So F is equal to A, B, C plus A prime plus A prime plus A, B prime, C. I want you to think a few minutes on it. And whoever solves this first, actually, I'm going to give them extra points on their next homework. I will give you a few minutes to think on this, and this is a pretty easy one, actually. Does anyone have the answer? Yes.
FS is equal to AC.
Oh, very close. AC, AC.
Yes.
Oh. Okay. Between these two terms, what is common between these two? Can I write it like this? AC and with B plus B prime. Can I write these two like this if I combine these two?
Did you also write it as A plus A prime? Or,
No, you can't, because we want to, that is a one, literal term. These are 3 literal terms. And all of that plus A prime. What is B plus P prime? What was X plus X prime? 1 always. So this is 1. So F is going to be equal to A C multiplied by 1 or times 1. And write it like plus A prime. What is X and with 1? It's X. So AC and with 1 would be AC. Plus what? A prime.
I guess what I did was wrong, but I factored out the A, so that A prime became 1 prime, which would be 0. Can you not do that?
No, no. Because maybe that's 1 and A prime becomes 0. But you can use this postulate over here. Sorry, I don't know why my pen doesn't work. Give me a second. So which one of these postulates can I use? Can I use X plus YZ? It's X plus Y and X plus Z. Yes. So X plus YZ is equal to X plus Y and with X plus Z. Am I correct? Yes. This is my X. These are my Y and Z. So AC plus A prime is equal to A prime plus A and with A prime plus C. Am I correct? Yes. Using that postulate. What is A plus A prime? And this would be multiplied by A prime plus C. What is X and with 1? This X, which is going to be what? A prime plus C. So the final answer would be A prime plus C. F would be equal to A prime. Is it clear? Can I go to the next one? I would solve a lot of these problems. Another property that we have in Boolean algebra, it's called the absorption property. For theorem number 6a, x plus xy gives us x. And the way that we prove it, we can write it like this. X plus xy is going to be equal to x and with 1 plus xy. And by postulate 4a, x and with this would be x and with 1 plus y. And 1 plus y is equal to 1. So it will be x and with 1, which again, x and with 1 is equal to x. And in the same way, we can show by duality that x and with x or y is going to be equal to x. And we can also, another way to prove these is using the truth table and just replacing the literals with the actual values, binary values of zeros and ones. So if x, y, and are 0, 0, again, x plus xy gives us 0. If it's 0, 1, it gives us 0. If it's 1, 0, it gives us 1. And if it's 1, 1, it gives us 1. And you can see that the result is the actual mirror of x. It's exactly equal to x. So it's going to have 0, 0, 1, 1, which is exactly equal to x. So one other way to prove these Boolean algebras is to replace the literals with the binary values. But if it's a very large equation, it's gonna take a lot of time to replace it. Like the previous one, you have to replace all the A's and B's and C's with 0, 1s to get the final answer. Okay, can I go to the next slide? So the next theorem that we have, which is very important, is called the De Morgan's theorem. And theorem number 5a shows, and all of these again are in this table that I shared with you here. That's the reason this is a very important table that gives us you all, and I would recommend that you could print this and bring this if you want to in your exams. And you can see here the De Morgan's law and the absorption law and so on, theorem and so on. What does De Morgan theorem say? It says x plus y prime is equal to x prime y prime, or xy prime is equal to x prime plus y prime. And by means of the truth table, we can actually prove this. So if you find, again, if you want to find the prime of an equation, just replace all the ands with ors, or all the ors with the ands, and zeros with ones. And here we can see that if we write the truth table for x, y, x prime, y prime, so x plus y prime gives us 1, and x prime, y prime also gives us 1. Therefore, they are equal. And you can see that anytime we have x plus y prime, it's equal to x prime, y prime. Now, let me give you another example. We want to reduce or simplify the following equation. F is ABC plus A, B prime plus C prime. I want you to simplify this. And again, I'll give you 5 minutes, and the first person to solve it gets extra points. Did you write it down? I want to go back to the table so you can use the table. Did you all write this down? Can I go to the table? Okay. Can use the theorem table and use any of these theories to help you solve the problem. Does anyone have the answer for this? Perfect, yes. That's correct, yes. Remind me to give you bonus point for it. So again, we can replace using De Morgan's law, B prime plus C prime. There are multiple ways, by the way, to solve this. This is not just a unique way, but this is just one way to solve it. We can write B prime plus C prime as B prime or BC prime. So F would be equal to A BC plus B prime C prime or B C prime. Now, what is X plus X prime? 1. And what is 8 and with 1? So the final answer would be the next theory that we have is called the consensus theorem. And first one is xy plus x prime z plus yz is going to be equal to xy plus x prime z. The second one is x plus y plus x plus y and with x prime plus z and with y plus z gives us x plus y and with x prime plus z using the duality rule. So for the proof of this, x, y plus x prime z plus yz, we can write it like as xy plus x prime z plus x prime, because x plus x prime gives us 1, and 1 times anything would be equal to that literal. So it's going to be equal to yz. And when distributing that, it's going to be xy plus x prime z plus xyz plus x prime yz. And we can write it like xy plus xyz plus x prime z plus x prime zy, which is equal to xy plus x prime z. And we can prove the other one using duality as well. Now, a note here is the operator precedence. The operator precedence for evaluating Boolean expression is first the parentheses, then the not, and an or. So for example, if we have x, y prime plus z, or x, y plus z prime. And I'll give you some more examples. Now for a Boolean function, we have binary values, binary operators such as or, and. Unary operators like not and parentheses. Some examples to solve: f1 is equal to x, y, z prime. I want you to simplify these. And f2 is equal to x plus y prime z. f3 is equal to x prime y prime z plus x prime yz, and plus x y prime. And f4 is going to be equal to x y prime plus x prime z. Now, I can solve this using the truth table. So for example, for f1, I can write a truth table, x, y, and z, and we have f1 as the answer. If x is 0, y is 0, and z is 0, what would f1 be? What would it be? 0. If x is 0, y is 0, z is 1, what would f1 be? 0, thank you. If it's 0, 1, 0, what would F1 be? 0, 1, 1. 0, 1, 0, 0. 0, thank you. 1, 0, 1. 0, 1, 1, 0. Are you sure? Z is 0, so Z prime would be 1.
Oh,
So it's going to be 1. And 1, 1, 1. It's going to be equal to 0. So only in this situation, F1 would be 1. In all the other situations, F1 would be equal to what? 0. And we can do the same thing for F2, F3, and F4. So if we write the truth table for 2 in the power of 2, 2 power of n entries, we have 3 entries, so we're gonna have 8 different possibilities. And you can see here for F1, it's gonna be 0, but if we have 1, 1, 0, it's gonna be equal to 1. And for F2, it's gonna be 0 when x, y, z is 0, but it's gonna be 1 when x and y are 0 and z is 1. And it's gonna be 1 when x is 1, no matter regardless of what y and z are. So just from this, we can realize that we can simplify it as f is equal to x plus or if it's equal to just f is equal to x, because when x is 1, f is also equal to 1. This is one solution that we have for this. And I'll explain how this is done. I don't want to confuse you at this point. And same thing, we could do it with F3 and F4. The only thing that we have to do is we have to write the truth table and replace the values, the Boolean or the binary values with these equations that we have here. Now we could draw the Boolean functions by implementing the logic gates as well. If I want to draw the logic gates for the first one, I have 3 inputs. I have x, y, and z. And how are they connected? X, y, and I have z prime. So I'm going to put a knot here, and I could connect all these 3 together and put them in an AND gate. So the output would be x, y, z prime. Now I want you to go ahead and do F2 for me. So for F2, we have X, Y, and Z. Y is ANDed with Z prime, so I put a NOT gate here, and I put these through an AND gate. So now here I have Y prime Z, and I need to just add it to X. So this is going to be X plus Y prime Z.
Why is the NOT gate on C?
Oh, I'm so sorry. It should be on Y. Why did I do that? Yeah. X, Z, Y. Thank you. I just mixed it up. That's on X, Y prime Z. And if I go back to that table, the truth table, and if I give X1, Y1, and Z0, you can see that Z prime would be 1, and the result here, 1 and with 1 and with 1 gives us 1. And you can double check it with your logic gates as well. Now let's do F3. I don't have enough space for this, so I'm just gonna erase it. So for F3, we have X, Y, and Z. So for the first one, it's going to be X prime, Y prime, X, Y, and Z. And Z, all of them connected to an AND gate. The second one, I have an X prime. I'm going to just connect it with blue so you can see what I'm doing. X prime, Y, and Z. These are also connected with an AND gate because we have X prime, Y, Z. And I'm going to do the last one with the green color. It's X prime Y. So again, I could connect this to an X prime. I'm sorry, it's X, Y prime. So connect to an X and connect it to Y prime. And both of these are connected to another AND gate. So this is X, Y prime. This is X prime, Y prime Z. And this is X prime, Y, Z. And all of them are added together, so I can have all of them added together, and this gives me F3. And for the last one, F4, we have X, Y, and Z, 3 inputs. X, Y, and Z. The first part, it's X, Y prime. So we would multiply X with Y prime. And for the second one, we have X prime Z. So I'm going to connect X prime, X with a NOT gate, to Z. These are going to be AND gate. So this is X, Y prime. This is X prime Z. And finally, they are connected with an OR gate. This is going to be F4. Pick. They've all been, yeah, connected here as well. Now I want you to give you a small practice. If X is 1, Y is 1, and Z is 0, what is F3 equal to? or let's find it for all three of them. 1, 1, 0, 1, 1, 0, and 1, 1, 0. We want to find f2, f3, and f4. Fx, y are 1, and z is 0. We'll give you a few minutes to think on it. So what is the result for the first one? We have 1. This would be 0. 0 and with 0 is 0. 0 or with 1 is going to be 1. So f2 would be 1. The second one, this would be 0. This would be 0. And this is also 0. So anything out here is 0. This is 0 also. We have 1 here. We have 0 here. So 0. F3 would be 0. Did you get 0 as well? And for F4, this is 1. This is 0. This is also 0. And this is 0. So 0. And this is 0. And F4 is also 0. So F2 is 1, F3 and F4 are 0. Now I have another question. Can I simplify F3? And if I simplify it, what would the result be for F3? I want you to simplify F3 using Boolean algebra, the theorem and the postulates. Can I combine these two and write it like this? F3 would be equal to x prime times y prime z plus yz plus xy prime. Can I write it like this? Yes. And I can do it again here as well. I could say this is z times y plus y prime. Yes. What is y plus y prime? 1. And z times 1 is equal to what? Z. So F3 would, so all of that is equal to z, would be equal to x prime z plus x y prime. Now, how many gates do I have here? 1, 2, 3, 4, 5, 6 logic gates. How many gates do I need here? 1, 2, 3, 4, 5. And this is one way. So we can reduce the number of gates using Boolean algebra. And that's the main reason we use Boolean algebra. Imagine you want to reduce, you can reduce the number of gates from 10,000 to 7,000. You're going to get rid of 3,000 transistors. You're going to make your computer much more efficient, consume less power, generate less heat, and so on. And I'll explain more in the next class how we utilize Boolean algebra to simplify our logic gates and the number of gates that we need in our digital design system. And I gave some examples here. I think it's enough for today, because the next part I have to do some algebraic, manipulation and solve some practice problems. On Thursday, we will continue with Boolean algebra and solve more practice problems. And we will also start our first class for the digital design lab. And we're gonna use the circuit design lab, the simulating tool, to be able to solve some real world, logic gate problems. Thank you so much, and I would see you on Thursday.